Hi, good morning, everyone. Welcome to ELSOC's DESN2000 Crash Course. I'll be your host, Jonathan, for today, and we will be running through the 2015 ELEC2142 paper, which was basically the precursor course to DESN2K before it changed the name. Okay, so first question, briefly explain what is meant by the three-stage pipeline in ARM7 TDMI. So basically, the three-stage pipeline just allows for the efficient execution of code in assembly through the fetch, decode, and execute pipeline. So basically, we have one stage for fetching data from memory, one for translation to machine code so that the CPU can understand instructions, and one for the actual execution that is stored within the code. Instruction, sorry, that is stored within the code. Yeah, I'll just quickly write it down. Is this recording? Oh, yeah, okay. Okay, so does that make sense? I'll take that as a yes. So state two main differences between the reduced instruction set computer and complex instruction set computer. So basically, I guess for RISC, this version of the computer has less instructions and is typically less complex to design with. But some other things to note are that all instructions within this computer are the same length, and that it uses the read, modify, write cycle for memory manipulation. Whereas for the complex instruction set computer, it's basically just the opposite, more instructions, more complex to design with. It has variable instruction lengths, and direct memory manipulation is allowed. Kind of like when we are working with GPIO, how we use pin over set vs clear. For the next question, it's just like unsigned ones complement and twos complement. So I won't be going over it if you've done because if you've done ELEC 2141, you probably know how to do this already. But just a quick refresher, all you would probably do is convert 0xe5 to binary and then to decimal. And then for ones complement, you'd invert all the bits, and twos complement is just adding one to your ones complement. And then now we consider the following ARM assembly code, which declares and initializes some runtime memory content. So here we have DCD 0xa315, DCB 0x22, and DCB 0x44. Does anyone know what DCD represents? Yep, so basically it just allocates enough space within the data section to store a full word, which is 4 bytes. And then let's just assume that the data points to the memory address 0x, whatever it says here. So we'll copy this out. And then increment by 1 byte each time. So do we remember if ARM uses little endian or big endian? uses little endian, right? So basically that means the LSB in the first case would be 15. The least significant bits would be stored at the address of the lowest value. So typically, while we initially might like write something like what? 0x00, 0x00, and then followed by 0xa3 and 0x15. That would be the big endian form where the LSB is stored at the largest address. But since we're using little endian, we actually invert this around 15, A3, 00, and 00. And then for DCB, because these only allocate 1 byte's worth, we can just continue them on here. So we'd write 0x22 here and 0x44. And that's basically what it would look like within memory stored. This is what the memory section of the data would look like. And now for this, it's slightly different. We have the align instruction here, right? So does anyone know what the align instruction does within the data section? No? Okay, so basically we are given like an offset of 3 and basically like, I guess, a starting position 4. So basically, when we write a line for 3, it will look for our address values that are multiples of 4. So in this case, if I copy this section out, because the beginning of the code would look the same, I'll bold the possible addresses which the align would align to. So 0x4 ending in 0, ending in 4. And then 8 would also be 1 as well. Align will take the smallest possible value. So basically, a multiple of 4, an address of the multiple of 4 with an offset of 3. If we add 3 to any of these, it would take us to 0x403, 7, or if there was 1, 11 as well, which I have italicized up here. And you can see here how that the smallest like address is actually 7. So this DCB that follows the align pattern would actually fill up this spot, which means that we'd have to have yeah. Yep. I'm pretty sure it is, yes. Oh, sorry, my bad. Yes, you're correct. Did I skip one? No, 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 it's still 9. Oh, yep. Got it. My bad. Sorry about that. Good picture. And then, yep, so that means the value at this address would be padded out to allow for this align. Did that make sense? You can type in chat if you want me to stop at any point. Nothing? Okay, all good then. So state 3 different ways you can update one or many of the condition flags in CPSR in the user mode of CPSR being the current program status register for memory. So one thing we can do is comparisons, which uses something like what? CMP R5 with you can use either a constant or another register. And this basically just subtracts value stored in the second argument from the first and determines carry flags from there. The next thing we can do is append S to the end of data processing instructions. So for example, if we do adds R0, R1, R2, not only will the operation be carried out by adding the value stored in R1 and R2 and storing it in R0. But basically, whatever comes from that addition operation will be stored in the status flags. And the final thing, it's a bit more niche, but shift operations actually update the carry flag. But it doesn't update the other flags because logically speaking, you wouldn't be able to. So if we do something like add R1, R2, R3, and then we do an arithmetic shift right, which is basically just like a signed integer shift, this will update the carry flag to the last bit that was shifted out. Although depending on the operation, it could also be the last bit like shifted in. Okay, and now let's consider this segment of assembly code. Write down the contents of R0, R1, R2, R3, and R4 in 8-digit hexadecimal format after the execution of the above instructions. So first of all, R0, load num R0. Let's just assume that the address is like 0x04000000, and that would be loaded into R0 after the first cycle. Yep, so I'll just write a note down here. 0x404000000 is address of label num. And then it'll just be the same for all of these. I'll just indicate these with an asterisk. And then now we load 1 byte from R0. So can anyone tell me if BB or AC will be loaded into R1? It'll be AC, right? Because if we're doing little endian and we're increasing like the address number, then it'll always start with the LSB. So in here, it'll be 0x00, AC will be stored. And then since it's not meant, R1's not used again, we can assume that the values are the same. For R2, does anyone know what this instruction stands for? So basically, this is like loading into a register a signed half word. And because there's an offset of 2, we start from, that's 1 byte shift, 2 byte shift. So it'll be 00BB. But, so we might do something like this. However, because it is a signed half word and B begins with 1, indicating that it's a negative number, we actually pad it with Fs before. And then this remains the same again. And then for R3, since it's just LDR, it loads the entire value of that's stored within num, which is just zero x wait, LDR R3 00, yep, 0x FFAC BB 00. And then for R4, we move R3 left logical shift right by 24. And 24 would indicate 6 bytes. So we end up with 0x000000FF. Yep, and that's basically our values for this question. Okay, and now we're up to question 2. Does anyone have any questions for the parts we've covered so far? Nope. Okay, I'll continue then. Oh, wait. Stupid. Oh, okay. Consider the following segment of assembly code. Yep, just a bunch of instructions. And then let's write it out. Okay, so for the first instruction, it's essentially just EOR is just an XOR, right? Between R0 and an R0 that's shifted to the rotated right by 16 bytes. I typically like writing out the actual values for each, so I'm just going to write it all in binary just so you guys can visualize it a bit easier. So this becomes 0B B 1100. Can we show this? Oh no, 1101, sorry. 400100100100 1100 0011 1010 0010 1001 and then 0001. So R0 and then for our other value, the one that's R0 but rotated right by 16 bits or 4 bytes, we would get 0B. You know what, for the sake of this, I'll just copy this out. Because we're shifting right by 16 bytes, it's essentially just swapping the first half and the second half of the number. So this equals 0B 0111 0110 0101 0010 0111 0110 0101 0010. So with an XOR, basically, if the digits are the same, then the output is 0. But if they're different, then the output is 1. And then for BIC, it's essentially just ANDing, but you're ANDing with like the inverse. So in this case, we're ANDing R1 with the complement of FF00, whatever it is. And 0B. So in this case, it would be 1111, 1111, 0000. And this means that R1 is now basically exactly the same as the original value, but with these two blocks, they're both just zeros. And then now we're moving a rotation of 8 bits or 2 bytes into, 8 bits or 8 bits or 1 byte, sorry, into R0 again. So R0 is just shifting these 4 to the beginning because it's a rotate shift right. And the final one is another XOR, which is going to equal, the last one is an XOR between R0 and the logical shift right of R1 by 1 byte. So we use the same value of R0 again. And R1, since it's a logical shift right, it doesn't care about maintaining sign, but even if it was an arithmetic arithmetic shift, because the MSB is 0, it doesn't need to carry 1s on. So we can delete the last 8 bits and pad the beginning out with 8 zeros instead. And now to get the XOR of this, we end up getting, let me have a look, 1001, 0001, 1010, 0010, 1100, 0011, 1101, and 0100, which actually equals, if we were to write it in hexadecimal, A1 B2. I messed up something. D3, D4. Yep. And you'll realize that, oh, okay, I think I messed up. I probably just wrote something out wrong, but this should actually probably be 10, and this one should be 11. But you'll probably realize, okay, if we redo that, 11, say that's 0, 1, 1, this would be 0 instead, and this one would be 0, 1, 1, 0. So still the same thing. Wait, 0, 1, 1, 0. And then if R1's here, one, one, one. Oh, looks like it wouldn't really have changed anything because those last 2 bytes were shifted. That last byte was shifted out anyway. Yep. Okay, so yep, we can see that basically with this number, it was just essentially reversed from B4 C3 B2 A1 to A1 B2 C3 D4. Did that make sense? I'll take that as a yes. Oh, shit. Okay, no, that's why. And yep. And then for the next question, what other you probably won't need to know floating points for your finals, so we'll skip over this and maybe come back to it later if we have time. So for part 3, translate the following ARM assembly mnemonics into the hexadecimal representation of 32-bit binary machine instructions. Use the information sheets attached. Yep, so basically in the exam, you'll get a data sheet which looks something like this, and you just kind of have to follow it to figure out what the instruction is. So here we have the first 4 bytes related to the condition. I don't have the sheet here, but basically this just represents what the GT sign is. And GT, I'm pretty sure, is represented by 1100. So, and then for the next 2 bits, we put in 00. And then next is the immediate operand. Basically, if an immediate is used, this is set to 1, otherwise it's set to 0. So in this case, you see how we have a constant value in the sign here. So we put in 1. And then afterwards, it's this operation code. We have a look. Since it's a move instruction, move is represented by 1101. So that's our next 4. And then following that is the first register, Rn, which is just a constant. So here we put 0, 0. No, we put, oh, I'm missing something, sorry. There was something in between the two. There's this set condition code. So basically, remember what we were talking about earlier about how we could set status registers by appending S to an instruction? Here, since there's no S, we just put 0 for that. And then because for a constant, I'm pretty sure the pseudocode just defaulted to using R0. So we just put 0, 0 for the bit with the first operand register, and RD is equal to R3. So we put 0, 0, 1, 1. And then for the lengthy section, the operand 2, we have a look at the stuff down here. So we can use this shift immediate shift length, 11, 10, 9, 8, 7, which is 5 bytes long. And what value are we shifting in? A5. This can be represented by 1, 0, 1, 0, and then 0. I'm missing something. 1, 0, 1, 0, 0. 6, 7, 8, 9, 10, 12, 18, 19, 31. Okay. I'm looking at the wrong one. Just hold on, give me a moment. I've gone 31 to 28, 27, 26, 25, 24 to 21, 20, 19 to 16, 16 to 12, and then it should be 11, 10, 9, 6, 5, 4, 2, 1, 0. Okay, so 12 bits for this. Yeah, operand. We don't have a second, so we use this bottom one over here. The shift apply. Oh, okay, got it. So our immediate would be, if we were to rewrite A5, it would be 1, 1, 0, 1, 0, A5, 5, 5. What is 5? 0, 1, 0, 1. That could have been put in as 1, 0, 1. 1, 0, 1, 1, 0, wait. 1, 0, 1, 1, 0, 1. Is that large enough? Rotate. 11, 8, 7. Oh, actually, because this is small enough to fit, we don't actually have to do all of that. We could probably just do a rotation of 0, 1, 2, 3, 4, and then chuck in A5 at the end, which is 1, 0, 1, 0, 0, 1, 0, 1. And that would be our answer here. And as a hexadecimal, this should equal 0, x, d, 3, 1, 0, 1, 0, a, 1, 0, 1, 0, and then 0, 0, 0, 0, 0, 3, another 0, and then the last two digits are a and 5. So typically we can load in like 8-bit registers, but 8-bit values into a register, but if we had anything higher, then you might have to consider the rotation operation here. And then for the next one, it's a similar thing. We'll just go through the table again. Oh, it's here, sorry. For anything without a condition, so for this case, it's just adding with an S appended. We just use the AL here. So the first thing is 1, 1, 1, 0. Again, 0, 0. Since there's no immediate or constant value here, we'll put 0 for I. And then the operation code, we get it to be 0, 1, 0, 0. And then S, since it sets a condition code, we put 1 here. And then our first operand register is equal to R1, so 0, 0, 0, 1. Our destination is 0, 0, the 0 register. And for operand 2, instead of using the rotate plus immediate, there's a shift involved. So we'll use the shift here. We will use the top one, I believe. So the shift is only 2, so we can write it out as 0, 0, 0, 1, 0, because the shift is a maximum of 2 to the power of 5 or 32-bit shift. And then the shift type is an LSL, so we put 0, 0 next. And then we put 0 followed by the second register, which is R2. So we end up having this in binary form, which is equal to 0x E 0, 0, 1, 0, 0, 1, 9, 1, 0, 1, 0, 2. Yep. And then translate the following hexadecimal code into the corresponding ARM assembly mnemonic. So let's write the binary of this first. So we have 0B 0B 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0, 0, 1. So let's have a look. 1, 1, 1, 0 is another ignore one. And then, so we won't have to append any condition at the end. For the next two, 0, 0, and then 1. So this does actually have an immediate value here. And then the opcode is 0, 0, 1, 0. So the operation is a subtraction one, as you can see here. And then after that is whether it sets the condition flags. Since it's 1, it does. Then the first register, or let me just write down what we have so far. So we have subs. Subs. Yep. First one would be n is equal to, what am I up to? Sorry. SRN is the first operand register 00100001. Did I mess up something? Looks like R2. And then the destination register is also R2. And from earlier, we said that the immediate was involved because of this 1 over here. And then it's just zeros followed by 1. So no rotation, and the immediate value is just 1. So it will look something like this. Does that make sense? Take that as a yes. And now write down some ARM assembly code required to compute fx equals the absolute of x plus 100 times x. Do this a bunch. So as a comment, assume x is stored in R0. So the first thing we'll do is compare R0 with 0. And then move if less than. Actually, no, we can do this later. First thing we'll do is break down how we will get 100 times x. So let's actually move R1. And we'll move R0 into here with a logical shift left of, I believe, 8. Because if we think about it, we can break down 100 into 64 plus 32 plus 4. Yep, which equals 2 to the power of 8. Am I tripping? Or is it 7? 2, 4, 16. Oh, is it 6? Sorry, 2 to the power of 6 plus 2 to the power of 5 plus 2 squared. And so we can just shift in with R1, R0, LSL 6, and then we can add R1 with R0, LSL 4, R5, sorry. Then add again R1, R0 with an LSL of 2 to get our 100x. And then now we can compare R0, the x value, with 0. Yep. Oh, yep, sorry. Add R1 to itself. And then compare R0 with 0 to see if it's positive or negative. And then we can add if it's greater than or equal to. We can store the value back in R0, I guess. So we'll add R1 and R0. But if not, we can subtract. If it's less than 0, if R0 is less than 0, we can store the value in 0 and subtract R1, R0 from R1. Yep. And there's probably more ways to do this, but this is probably the approach I thought of first. Does that make sense? Yep. Okay. Next question is explaining what pre-indexing and post-index addressing is. So basically, pre-indexing just involves incrementing / decrementing the value, the address, before obtaining address or values stored at the address. And then post-indexing just involves involves obtaining the address before changing the value of, let's just say, program counter. So for example, a pre-indexing would look something like LD loading A2, A1, #4, and then with the exclamation mark at the end to indicate that it will be indexed. This operation occurs before you load the value. And then for post-indexing, an example would be loading into A2, A1 first, and then adding 4 after. Yep, adding 4 after you obtain the value stored at A1. Changing the address. Yep. And then describe 2 different ways you can load a memory address into a register. So the 2 different instructions for this would be using ADR or LDR. So if we're to have something like ADR address and then a label, this would be rewritten as add A1 PC and then whatever offset is required to get this label. But a key note for the ADR operation is that the label needs to be within 255 words of the instruction. As for LDR, the assembler will replace this instruction with like a MOV or MVN operation. So basically, for anything that's like, I'm pretty sure 8 bits in length, any address or value which is 8 bits in length. And then otherwise, it uses LDR, whatever, and then like PC offset to obtain the value from a nearby generated pool, literal pool. Oh, it says to put instructions there, examples there. ADR. Oh, we'll just do R0, it's fine. PC, #5. I mean, no, label. And then for LDR, we'll use the equal sign to get the actual address. Yeah, so you can see here how ADR just directly obtains the value stored at the label or the actual label itself, and then LDR gets the address, so uses the equal sign. And now write down an equivalent. Okay, so this one, I don't have the actual question on this document here, but basically what this question entails is, where is it? Okay, so I'll just quickly write it here. Oh, sorry, it is here. I didn't see it. My bad. Yeah, if A is greater than or equal to B, then D equals A plus B, else D equals A minus B. So here, I'll just copy this a few times. So we can compare R0 with R1, which performs a subtraction, comparing R0 to R1. Let's just say compare A, R0 with B, R1. And then we can just add them if it's greater than, if R0 is greater than R1. And subtract if otherwise. R0, R1. Yep, that's simple enough. And now, so that was for if A, B, and D were 32-bit signed integers. Now for A, if they are 64-bit, typically, if you remember COM 1521, there was like a special register for multiplication between two values in case it overflowed. So known as the high and low registers, where high would store like the MSBs and the low would store the least significant bits. So I'll just arbitrarily name them. To be this. So first step, we would be to compare both of the MSBs, so R0 and R2. Compare R0, R2. And then if they are equal, we will now compare R1 and R3. The logic behind this is if like the first 32-bit, if the first part of the half of the number A is greater than first half of the number B, then we know that A is greater than B regardless of what these two values are. And vice versa, if A is less than B, like R0 is less than R2, then it doesn't really matter what these two values are. We only care about if those two are equal. Then we'll compare with the last two. So next step would be to BOT to a branch. Let's just name it sub. If I type I'll reformat all of this later once the crash course is done, but yeah. So sub. For sub, we will subtract store in R5. What was it? R1 minus R3. So R1 minus R3. And basically, if there is a carry error, so as in like R1 gets a carry in from when it subtracts R3, we will have to branch so the C just means carry in this case. I believe, let me double check. The C, it will be CS. Yep, so C is set. It would be CS here. R4. R0. R2. And then branch. Oh, no, we'll just leave it here. We'll just say end. And then as for the previous bit, we'll add the stuff together. Add to R5. R1, R3. R4, R0, R2. Oh, wait, no. Yep, okay. So actually, I got this bit wrong, sorry. So basically, ADC and SBC basically mean add with carry and sub with carry. So basically, when you set the condition flag up here, it will determine whether there's a carry or not. And then these operations underneath will add or subtract with that carry in context. So, and then we just branch to end. And that should be how you solve the 64-bit version. Let me just check if the data sheet has any mention of the carry ones. Yep. So you see here how there's an ADC and SBC operation there, where it shows that it adds the carry, or for in this case, adds the carry -1. Yep. So you can use that to make this a bit easier, rather than manually finding the carry and then just adding 1 or subtracting 1 extra. Okay, next question. Basically, we're just going to analyze this program and have a look at what it does. So if we go through here, loads in this array, move a constant into R1, so it's probably going to be a counter or something, and then we branch and link to the function here. And then it stores R5, R6 just to preserve the variables that's going to be changing later, because you can see here how it's the callee's duty to save like variable registers to the stack just to preserve their values afterwards. Then move R5, 0. So the first thing we do is load into R6 the thing stored at R0, 0 array A, with an offset of 4. And then we compare, oh no, and then we load in R0 and then we increment by 4 afterwards. That's because this is a post-indexing thing, not the usual pre-indexing we're usually used to. And then it compares R5, which is currently 0, to R6. And BCS means branching if R5 is greater than or equal to R6. Otherwise, we move R6 into R5. So since 0 is smaller than any of these unsigned values, R6 gets moved into R5. And then it continues doing this loop until, what's it called? R1 dips below 0 and becomes an unsigned integer with a value of it becomes a signed integer with a value of -1. Basically, what this program does is it compares like the elements from the array, and then it stores in R5 or R0 and returns the highest valued unsigned integer. So it returns the highest value unsigned integer in array A. And then if we go back up here, it says move R2 to R0. Move R0 to R2, address, read from address R0 array, and then store R2 in R0. But since this is pre-indexed with the value inside the square bracket, what's it called? Store this at an offset of 28 bits, or 0. So this would be the 0, 4, 8, 12, 16, 20, 24, 28 in array A, and stores the value in the last element of the array. That's basically what it does. And then what are the contents of register R2? Yep, so if we have a look, you can probably manually calculate it out, but typically the ones with the highest values at the MSBs would be the greatest value. So in this case, FF is the highest value. So R2 equals this. And then the 8 words in memory starting from label array A. So I'm not going to rewrite all of them because most of them will be the same except for one value, which is the last entry. So all array entries contain the same value except for the last entry, which is changed to the greatest value as we mentioned up here. So 0x FF and then followed by a couple of zeros. Okay, did that make sense? I'll assume it did for all of you. And now, okay, so here we're looking a bit more into like exceptions and interrupts, and we want to briefly explain the steps involved when the ARM processor handles an exception. So first step, so these steps are usually just handled by the ARM processor without you having to manually do anything. So the first thing is that it saves the user mode, like CPSR, into the SPSR of whatever mode you've switched to, because there are a couple of different like interrupt modes, or not just for interrupts, but like exception handlers that you can jump to depending on your type of exception. And then it modifies the appropriate bits of the CPSR to whatever mode or like stuff you want to use, such as like, I guess, IRQ or FIQ. There are a couple of bits you might have to select in order to set those. And then it puts the return address in the link register of your mode, and then loads the program counter with appropriate handler address from the vector table. And then it will jump to like whatever mode you want, and then it will carry out the exception code from there. Carry out exception handling code. And then once that's done, it will return to core. But when it returns to core, it does two things. Restore CPSR from the SPSR of your current mode, and restore PC from the link register. But both of these steps are done simultaneously. Okay, any questions on the processor? Nope. Okay, we'll move on then. So next, we're going to explain a bunch of other terms. These are all related to exceptions, except I guess maybe memory mapped input and output. But yeah, interrupt-driven I/O, software interrupts, and a vector table. So memory mapped input and output involves storing memory and input-output devices in the same address. So similarly to the GPIO pins, the GPIO you have been working with on in your DESN2000 labs. And then, yep, so the input reads a sequence of bytes, output involves writing a sequence of bytes back into a register. And input-output devices have registers for status and control and data. Which just determines whether they can be read or written to, and data just holds the value. It's similar to like your direction and your pin values. So with interrupt-driven I/O, there's another type, I don't remember the exact name, but you either have like polling or interrupts for like executing different code. And basically, this is just a method of triggering an action when a device or data source sends a signal to the CPU indicating completion rather than having to be continuously polled to check the status. And then after interrupt service routine completes its data transfer, CPU resumes subroutine from before the interrupt was called. So with like interrupt-driven I/O, because it only like, I guess, activates or is triggered when the device or data source indicates its completion rather than having to be continuously checked, it requires like significantly less like memory or processing power from the CPU. And I'm pretty sure in week 8, there's like a couple of questions regarding like how much memory polling versus interrupts use. And yeah, it falls under this interrupt-driven I/O. And then software interrupts are just a user-defined exception raised within the application by the CPU through, I believe it's the SVC instruction. It used to be called SWI, but I think newer models use SVC, or it might be the other way around. And these are known as synchronous exceptions, which occur within the CPU rather than manually resetting or switching, like I.E. using a reset button would be asynchronous. And yeah, these are handled when the when the program is in supervisor SVC mode. And then finally, a vector table is just an array of addresses with the first entry being the initial stack pointer after a reset, followed by the addresses of a list of exception or interrupt handlers. And when an exception occurs, PC is automatically loaded with the matching exception handler's address within the vector table. So typically, so I'll just list them out right here, but it will be like reset undefined instruction, software interrupt, prefetch abort, data abort, reserved, IRQ, so interrupt request, and FIQ is, I think, fast interrupt. Yeah, fast interrupt requests. So yeah, as we mentioned, oh, well, I didn't mention it earlier, but reset usually is stored at like 0, 0. And then it goes up by increments of 4, as we usually expect with addresses. Bit B, 8, 9, A, B, C. X10. And then no, some of these I'm pretty sure aren't actually stored within this specific address, but use like literal pools or other loading values, loading operations in order to grab the exact value stored within the address. Yep, so that's basically what a vector table is. Now consider this segment of ARM code. The code, and it contains 2 pseudo instructions. So for the first instruction, LDR is translated into I believe MOV with an offset. No, not that one, sorry. LDR is translated into LDR R1, program counter. Actually, I'll just write it here. As mentioned earlier, this was one of the ways that we could write an address into a register. And then for the second one, we would load LDR R2, but instead of using this PC, we could just do an MOV, like a move of how much? 0x7f, and then a left shift of 1, 2, 3, 4, 5, 6, 7, 8, no, 6, 24. Oh, wait, no. Okay, sorry, my bad. For load, for like the load instructions, it's actually not, it doesn't actually use LSL, like a logical shift left. It uses a rotation to maintain the value. So we end up getting actually a rotation to the right by 8 bits. So if 7F was here, those two values would move to the MSB. Yep, okay. And then determine the value of the condition code flags during the execution of the CMP instruction. And remember that CMP is like, what's it called? A subtraction. So I'll write it out in binary first just to make it easier. So we get 1, 1, 0, 1, 1, 0, 1, 0, 7, 0, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 7, 0, 1, 1, 1. And then for R2, we end up getting what? Zero B, 0, 1, 1, 1, followed by a bunch of zeros. And then R1 minus R2, all we have to do is choose complement this value. So 0B. So R1 minus R2 equals, we'd add this to this value up here. And that should equal 0B, 0, 1. Oh, I'll just write it out. Third, yeah, second, 0, 1, 0, 1. Choose. Should be probably 1 here. And then, yep, everything else is like that. And then for the status flags, we see that since 0 is the MSB, it's not negative, so that's set to 0. And because it's not equal to 0, that the 0 flag set to 0. Carry, we had a carry out because if we add 1 and 1, there's a carry out there, so that's 1. And we also have an overflow because if we see here, we have two negative numbers, 1 and 1. But then when we added them, it becomes positive, or it's like equal to the XOR of the carry out and carry in. So the overflow is also equal to 1. And then based on, yep, the XOR of the carry out and carry in, because carry out is 1, but carry in is 0, that's equal to 1 as well. And then based on these condition flags, which of these conditions would be executed? Okay, so for this one, we'd probably have to go back up to the flag here, the data sheet here. And if we have a look here, you can see that the flags are set depending, no, the instructions are carried out based on which flags are set. So for the first one, it was add LT when n is not equal to b. From memory, we had n equals 0, but b equals 1. Yep, so add LT will be carried out. And then there's a GE. Where n equals b, obviously that kind of just contradicts LT. So we know that GE won't be carried out. And then HI, HI is when C is set and Z is clear. Yep, so the instruction with HI condition would be carried out. Honestly, there's probably a faster way to do this. If we go back up here, just have a look. Oh, not here. Yep, so LS is given by C set or Z set. C clear or Z set. So from memory, C was set and Z was cleared, so LS wouldn't be called. For NI, I believe this should actually be MI here, or negative. And that's when N is set. So obviously, since it's not negative, and this wouldn't be carried out. BHS, HS would be representative of the unsigned higher or same. So the CS one where C is set. And in this case, we know that the carry was set, so BHS would be carried out theoretically. And then for greater than, it's asking for Z clear and N equals V. So Z is clear, but since N is 0 and B equals 1, greater than would not be carried out. So from these, only this one would be carried out, and the rest would not be. And now if the CMP instruction is replaced by TEQ, which condition code flags from part B will be changed, and find the new condition code flags. Yep, so if we go back up here, we can see that TEQ represents set condition codes on the XOR of operations 1 and 2. And now for XOR, we don't really have a carry or overflow because there's nothing being like shifted out or into the actual result. So B is not modified and C is also not modified after TEQ is carried out. And then if we XOR these together, 1, 0, 0. You can see negative is set, but the 0 flag is still 0. Okay, now we consider an ARM assembly subroutine function 1, which calls function 2. If both of these are AAPCS compliant, state one responsibility and one right each of these have. So the caller responsibility is putting any arguments / parameters into A0 to A3 and storing additional ones on the stack. As for the callee, it is to preserve any values stored in S0 to S7 or the variable registers. S7 or S8, I don't 100% remember, but yeah, just to preserve the variable register values. Storing these in the stack before running subroutine. And then as for a write, caller can expect any values from S0 to S7 to be preserved. And for the callee, it has the right to modify. Oh, is it A0? It's A1, sorry. A1 to A4, S1 to S8, modify A1 to A4 without preserving values. Yep. And then for this, it's asking us to explain the push and pop operations related to a full descending stack. Okay, so with a full descending stack, typically, actually, let's just keep this up here. No. So in the current stack frame, let's just say we have R8 stored here. And then in the next frame, the first thing the stack pointer will do will move down by 1. Oh, this is when we're like pushing in an array of values. And then R7, move it down. R6, and then in the next cycle, it'll move down again and store R5. And then it'll keep doing this until all your registers, or like the values of the registers, have been loaded in to the stack frame where it rests here. Keep in mind that this is like highest address. So for a full descending stack, when using push to save a register value, when using push to save a register value, the program counter decrements by 4 before storing the value in the stack. So pre-indexing. And then when we're popping a value, we remove this from the stack, or not remove it, but like we set it back into pop it to a register, and then the stack pointer gets shifted upwards where it still rests at a full head. So highest address. When using pop to obtain a register value, the value is loaded from the, oh, did I say program counter? Sorry, not program counter, stack pointer. Stack pointer, SP, yep. From the stack pointer's current address before incrementing by 4 bytes. And this just maintains like the full head. And then for here, for an empty ascending stack, it starts off with like an empty head first. So when you're like pushing a value, you will push like, let's just say R8 again first, and then the stack pointer moves after. So here, the stack pointer moved first before like you save the value to the stack, but for the empty ascending case, the stack pointer moves after you obtain the value. So it's a post-indexation essentially. And if we keep continuing this, R7, 6. R5, and then so on. Stack pointer rests at an empty address. Yep, so it's a similar explanation, but for an empty ascending stack. When using push to save value, the value is stored within the stack before the stack pointer increments by 4 bytes. And this is similar to what we covered earlier in post-indexing. When using pop, the stack pointer decrements by 4 bytes before loading the current value into a register. And here it asks, it should contain which STM and LDM we should use. So this uses STM. Full descending is like, what's it called? STM DB and LDM IA. ARM uses the full descending version of stack frames. Yep. And then for a empty ascending, uses store increment after and load multiple decrement before. Opposite of full descending. Okay, and now there's another coding question. So basically, if we have a look, it gives your 4 arguments stored in this order. Yep, V1, V2, V3, V4. Subroutine must use Gauss's multiplication algorithm to compute the product of the two numbers. And the return value of the subroutine is 1 if imaginary part is 0, so if P1 or P2 is 0. Otherwise, return value is 0. So technically speaking, we don't actually need to calculate the whole thing to find the return value because we only need to calculate P1 and P2. But I'll go through the method where we assume to calculate P1, P2, P3, since it wants you to use Gauss's multiplication algorithm to compute the product. So let's start by saving everything the registers we'll be using to the stack. STM, full descending, decrement before. SP, the exclamation mark indicates that it changes afterwards. What was it? V1, V2, V3, V4. Let's just say V5 to V7, because we'll probably need one for each of these values. And remember that storing and loading multiple isn't actually a pseudo instruction, only if you're doing like, the full descending, empty ascending, like those types. And then LR. And then the next step would be X2. So let's compute P1 first. P1 equals V5, P2 equals V6, P3 equals V7. So first, we probably want to add x1 and y1. Wait. V1, 2. Oh, it's probably, okay, yeah. We'll assume that they're the caller passed in the 4 different arguments in that order. So, because V1, V2, V3, and V4 are variable registers, I believe. So these probably would have been saved into the stack frame by the caller, which, since we're not directly modifying those 4, it's okay to not save them. A1, not A1, sorry. This one is V5. A1, and x1 plus y1 is A1 and A2. And then we can just use mul for this case. There's no restriction stopping us from doing that. And multiply V5 by x2, which is stored in V3. And then for these ones, we can probably do a similar thing for the other 2 values. So for P2, we have y2 minus x2. Y2 would be stored in A4, x2 would be stored in A3. And then we'd multiply V6 by x1, which is A1. And then for V7, we would add x2 and y2 again. Sorry, this should be subtract. V7, A4, A3, A4. And we would multiply V7 by y1, which is stored in A2. And then we'll just move. Actually, for the real component, it's P1 minus P3. Let's store that in V6. P1. So P1 minus P6. P6 equals real component of multiplication. And then we would add and store in V7. P1 plus P2. So V5, V7. V7 equals imaginary component of multiplication. And it says return value of the subroutine if 1 is the imaginary part. I mean, if the return 1 if the imaginary part of the result is 0. So what we can do here is add And then, because this saves the status flag of like the register of the stuff here, we can do move EQ. Because EQ will check if it's like, oh, is this value equal to 0, essentially. So if V7 is equal to 0, let's move this back into A1. I believe, yeah, A1 is R0, which is the value that you always move your return value back to. So with EQ A1 hashtag 1, return 1 if imaginary component is 0, and then move, we use NE for not equal to 0. Return 0 if imaginary component is non-zero. And then we'll load these back into their respective registers. Yep. And then move BC LR to just call the previous stack frame. So obviously we technically didn't need to do these, but I just went through them anyway. But yeah, the only important one was actually just calculating P1 plus P2 to see if that was equal to 0. Then you can get the return value. And then I believe this is the final question, but briefly explain the function of LT-org and DCW. Yep. So we'll probably start by explaining what DCW is. DCW, I believe, represents reserving a half word's worth of space within the data section of a program and stores the following expression within this space. It's a bit trippy because W looks like it would stand for word, but DCD stores a word. Yeah, I don't know why they do this, but it's just convention. And then for LT-org, this tells the code to build a literal pool where the label, or not label, the directive is called. And typically, it is best to put this at the end of the code section of following an unconditional branch. Because let's say, I'll give a short example here. Let's say we have like add R1, R2, hashtag 5, and then you had like an LT-org here. The org. So LT-org constructs a data section essentially, which if the program encounters while attempting to execute instructions through the pipeline, it might crash, since this is a data section rather than code. So yeah, it's best to modularize your code in case you want to like include like a bunch of literal pools within it, and also to add them at the end of your code or after something like these. Yep. I believe that is the entire paper for at least all of the relevant parts, because I don't think you'll be covering floating points in your exam. So that should be fine. And we still have a bit of time left, so I'll go over any questions I skipped. Okay, we'll do this one. What is this value as an 8-bit unsigned number? 0b, so E is equal to 1110, and then 5 is 0101, which equals, I can't be bothered to calculate this. Let's do it. 1 plus 4 plus 4, 8, 16, 32 plus 64 plus 128. And that's what? 37, 101 equals 239, I think. What is it? Oh, 229, 64, 6. Oh, yeah, my bad. 229. Then an 8 bits, one complement number. We remember we inverse all these bits. 0b 0, 0, 0, 1, 1, 0, 1, 0. This would equal 1, 2 equal negative 2 plus 4, 8 plus 16 equals negative 26. And for 8-bit 2's complement, it would be 0b 0, 0, 0, 1, 1, 0, 1, 0 plus 1 equals 0b which equals negative 27. And I guess that's it. Thanks everyone for coming to the crash course. I'll be sure to send out this document to everyone who's signed up after, once I make a few edits, and good luck with your final exam.